This is MSJ Chem. In this video, I'll be looking at areas of difficulty for the higher level. So we'll start by looking at Paper 1, Areas of Difficulty. The first point is Lewis structures. It's important to remember for higher level that students need to be able to draw Lewis structures for molecules or ions with up to 6 electron domains. Next, we have organic synthesis reactions. The challenge with this is that there are many organic pathways that need to be learned. I recommend reviewing my video on reaction pathways. Next, we have EZ nomenclature. With EZ nomenclature, you assign priority to each group bonded to the carbon atoms of the carbon-to-carbon double bond based on atomic number. Next, we have identifying when oxygen is reduced in a redox reaction. For example, oxygen can undergo reduction in an acidic solution to form hydrogen peroxide. Next, we have mathematical calculations without a calculator. This is especially important for Paper 1. In Paper 1, calculators are not allowed. Next, we have ranking d orbital splitting in a complex ion according to its color. The larger the energy difference between the two sets of d orbitals, the shorter the wavelength of light that is absorbed. Next, we have understanding how number of valence electrons influences strength of metallic bonding. So basically, the greater the charge on the ion, the larger the number of valence electrons, and the stronger the metallic bond. Next, we have being able to calculate kilojoules per mole when the reaction is not balanced to 1 mole of reactant. Next, we have understanding how rate constant varies with temperature. So an increase in temperature increases the value of the rate constant. And finally, for this slide, we have being able to distinguish between amphiprotic and amphoteric. Amphiprotic is only used for Bronsted-Lowry theory of acids and bases. The term amphoteric can be used for all theories of acids and bases, such as Lewis theory. Next, we have using the Kelvin scale when dealing with the gas laws. So when using the ideal gas equation, Charles's law, Boyle's law, or Gay-Lussac's law, temperature must be converted into Kelvin. For example, 25 degrees C is 298 K. Next, we have comparing the ionization energies of ions. Next, we have entropy and free energy values at equilibrium. At equilibrium, entropy is at its maximum value and free energy is at its minimum value. Next, we have salt hydrolysis. Whether a salt is acidic, basic, or neutral depends on the parent acid and base. Next, we have relating the color of an indicator to pH and its pKa. The next 3 points, identifying oxidizing and reducing agents in a disproportionation reaction, oxidation of alcohols, and the structure of benzene, were all covered in the areas of difficulty for the standard level. Next, we have comparing the rate of hydrolysis of different halogenoalkanes. This is dependent on the strength of the carbon to halogen bond. As we go down group 17, the carbon to halogen bond gets weaker. A weaker bond results in a faster rate of reaction. Next, we look at Paper 2, Areas of Difficulty. The first point is stoichiometric calculations involving percent composition and mass calculations. It's important that students know how to do basic calculations involving conversions between amount in moles, mass, and molar mass. Next, we have most energetics calculations involving delta HF, enthalpy, bond enthalpy, and entropy. This is mainly topic 15. That topic is very calculation heavy, so I recommend students practice examples from past exam papers. Next, we have identifying bonds responsible for signals in a H1NMR spectrum. This topic is one of the most difficult concepts in topic 11 and 21. Next, we have writing equilibrium expressions. They take the form of Kc with the products in the numerator and the reactants in the denominator. Don't forget to raise the concentrations of the reactants or products to the power of the coefficient. Next, we have explaining and predicting physical properties based on intermolecular forces. These involve mainly melting and boiling points. The 3 types of intermolecular forces are London dispersion forces, dipole-dipole attractions, and hydrogen bonding. Hydrogen bonding is the strongest of the 3. Next, we have balancing equations. I recommend students practice this using the worksheet on my website. Next, we have estimating pH of solution. At 298 K, acidic solutions have a pH of less than 7, and basic solutions have a pH of greater than 7. Next, we have stating environmental impact of acid rain. This is mainly focused on the reactions with calcium carbonate. So I recommend students are familiar with writing equations of both sulfuric acid and nitric acid with calcium carbonate. Next, we have predicting difference in rates of reaction with a strong or weak acid. So a strong acid will have a faster rate of reaction with an active metal, such as magnesium, than a weak acid of equal concentration. Next, we have redox reactions and electrochemistry of voltaic cells. This is topic 9 and 19. Next is deducing polymer repeating structure from a monomer of ethane. If we're talking about addition polymers, this should be ethene, so I think there's a mistake in the subject report. Anyway, this is covered in topic 10. Next, we have explanation of processes such as how to find atomic mass from a mass spectrum, understanding of why TMS was used and is still the reference in H1NMR, how to monitor rate of reaction, and how to determine activation energy. So all I can recommend here is that you thoroughly review these topics. Next, we have predicting electron domains and molecular geometries. Remember, for higher level, this could be for molecules or ions with up to 6 electron domains. Next, description of how sigma and pi bonds are formed. Sigma bonds are formed by head-on overlap of atomic orbitals. Pi bonds are formed by sideways overlap of atomic orbitals. Next, we have arithmetic errors and incorrect signs in calculations. All I can recommend here is that you double check your calculations. Next, we have explaining using appropriate equations how a buffer solution works. For buffer solutions, you should know how to write equations when either an acid or a base is added to the buffer solution. Next, we have writing equations involving Lewis bases. A Lewis base is an electron pair donor, and a Lewis acid is an electron pair acceptor. Next, we have identifying similarities between SN1 and SN2 reactions. Similarities include the type of bond fission, which is heterolytic. Next, we have explanations of bonding, such as the nature of an ionic bond or why calcium can conduct electricity. So an ionic bond is the electrostatic attraction between oppositely charged ions. Metals can conduct electricity because they have free-moving, delocalized electrons. And finally, we have emission spectra. Emission spectra are formed when electrons transition from higher to lower energy levels.